Today we're going to look at some of the functionality for your graphing calculator for your TI-84 or TI-83 if you have a TI-83 that you're going to need for the AP test. And I'm going to run through some of the processes on the calculator and also just talk about what they're looking for on the calculator section with the AP test. So one of the things you're allowed to do with your calculator on the calculator section of the AP test, and for any test in my class, is to evaluate the derivative of a function at any given x value. So this will be the easiest thing that we're going to do today, probably. We're just going to use our calculator to find the derivative of f of x equals x squared ln x sine x at x equals 3. And we'll note that it says we're going to round our answer to 3 decimals. On the AP test, you will never round to less than 3 decimals in your final answer. And if you are using intermediary values that are not part of your final answer, don't round them at all. You can also leave answers longer than 3 decimals, but if you're going to round, don't round to less than 3 unless it specifies otherwise. So in order to do this, the first thing you got to make sure you do is on the AP test, write out exactly what you're having the calculator evaluate. So you're going to write the derivative with respect to x of x squared ln x sine x evaluated at x equals 3 equals. And then you're just going to use your graphing calculator to figure out what that value is. So I'm going to pull up my graphing calculator here. And the first thing I want you to know how to do before you learn how to take a derivative is how to just completely reset your calculator. So in order to completely reset your calculator, which is kind of convenient if you're sitting there in the middle of the AP test and you keep getting an error and you can't figure out why, or you can't see the graph for some reason, just hit second, then the plus sign, which brings up the memory window. You're going to choose option 7. You can either go down to 7 and hit enter, or you can just hit the 7. And then you're going to choose option 1, and then option 2. And this will reset everything on your calculator back to the factory set. That means it's going to put your calculator into radians. If you look in the mode window, you can see there's an option for radians and degrees. If you start doing stuff with trig functions in the degrees mode, you're going to end up with the incorrect value. So you always make sure you're in radians. So one of the ways we can find this derivative is we're going to hit the math button. And then under the math window, there's option number 8. Option 8 says in deriv. We just hit 8. If you've got a newer calculator, it's going to pop up a window that looks just like what we wrote on the previous page. And if you don't have a newer calculator, it might just say in deriv with a parenthesis, and I'll show you what to type in for that. But for this, we just need to put an x, which is next to the alpha button. And then we need to type in our function, which was x squared times the natural log of x. Make sure you close the parentheses after the x, times the sine of x. We'll close that parenthesis. And we'll go over here to where it says x equals, and we'll put in the value we were trying to evaluate it at, x equals 3. And we'll just hit enter. And we end up with negative 8.43498,583, which will round to negative 8.435. All there is to finding the derivative of a function at a point using your calculator. We'll do another one really quickly just to make sure we got the hang of it. This one asks us to find the derivative of the inverse cosine of x cubed times log base 10 of x squared. So we'll pull up our calculator. And we are looking for, again, the math window. Option number 8 in deriv. We'll put an x down there. We'll put in our function, which is the inverse cosine of x to the 3rd power. And you can get the 3rd power either by hitting the caret little button up there, and then a 3, which you'll have to hit a button to the right on the newer calculators to move out of that. Close your parenthesis. Or to get a cubed, you can go in the math window, and it's option number 3. So we've got the inverse cosine of x cubed times the log base 10. And remember that log base 10 is sometimes just written as log with no base there. If it just says log, that means common log, which is log base 10, then of x squared. And we wanted this at x equals 0.45. We'll just evaluate that there. And we get 3.278925135. So we could say the derivative with respect to x of inverse cosine x cubed times log base 10 of x squared at x equals 0.45 is 3.278925135. We could leave it like that. It specifically asked us to round, so we'll make this 3.27. And if you're one of the people that has an older calculator, and when you hit in deriv, it just pops up saying in deriv with a parenthesis, it's pretty straightforward. All you got to do is type in the function, inverse cosine x cubed, log, and your calculator won't say base 10, so we'll just say log of x squared, close your parentheses. Oh, not close your parentheses, this is the other way. Put a comma, and you can find the comma, I believe it's above the 7. And then we'll type in x, and then another comma, and then we'll type in the value that we're looking for, 0.45. And we'll close our parentheses, hit enter, and you'll get this exact same value. All right, here we're looking at the graph of y equals -2 plus e to the tangent x crosses the x-axis one time on the interval 0 to 1. We want to find the slope of the graph at that point. So first off, we think, what are we trying to find here? We're trying to find the slope of a function, which means we need a derivative. We're trying to find the derivative when it crosses the x-axis on this interval 0 to 1. So what we're going to do is first find the x-intercept. So we're going to set -2 plus e to the tangent x equal to 0. Now, we could solve that by adding 2 and taking a natural log and an inverse tangent. Or because I'm telling you that this is a calculator question, we can let our calculator approximate this value. So if you're going to approximate an x-intercept or a solution to equation on your graphing calculator, you need to write what you're having the calculator do, -2 plus e to the tangent x equals 0. And then we will go in to our graphing calculator. We're going to hit y equals to graph it. We'll type in the function -2 and make sure you use the negative sign, not the minus sign. If you get the minus sign instead of the negative, it's going to give you an error. So we're going to have -2 plus e to the x is second natural log, and we'll just put tangent x up there. And to look at the graph, we just hit the graph button. And we can see this is what we get. And we're looking for the x-intercept between 0 and 1. Now, in order to find that, there's a whole thing inside the second and then trace menu, second calculate. But before we do that, we're going to take a couple of steps that aren't super necessary for this problem, but just to help us get familiarity with the graphic calculator. So we're only interested in what's going on the interval from 0 to 1. So sometimes it might be helpful to know how to change your window so that you're only looking at x equals 0 to x equals 1. We're going to hit the window button. We got a whole long list of things where you can see you can change minimum and maximum x values and minimum and maximum y values. We're interested in the minimum x value being 0 and the maximum x value being 1. So now when we hit graph, it just shows us with the y range unchanged what's happening between x equals 0 and x equals 1 for this function. You can also get your graph to stretch out using the entire vertical space, but still keeping the x range the same, which can be helpful sometimes also, by hitting zoom. And then you're going to go all the way down to option 0, zoom fit. And if you hit enter on zoom fit, it kind of stretches it out. Good. now that we've got a really clear picture of what's happening with this function from x equals 0 to x equals 1, we're ready to find the x-intercept. We're going to hit second and then trace, which brings up the calculate window. And we're looking for when does this function equal 0, or when does it have an x-intercept? That's option number 2. We're going to choose option number 2. It's going to bring us back to the graph with a cursor flashing somewhere on it. And it's going to say left bound. What that's asking you to do is to put a left boundary on where you're looking for your x-intercept. So since my cursor is already to the left of where that x-intercept is, I can just go ahead and hit enter. If it wasn't already to the left, you just use the left arrow key so you get over to somewhere to the left. You just go over to the left. So since we're to the left, I'll hit enter. It then switches and says right bound. You're going to hit the right arrow key a bunch of times so you are to the right of where that x-intercept is. You'll hit enter again. It'll then say guess. And when it says guess, just hit enter a third time, and it will tell you what that 0 is. In this case, 0.6061119. So we'll go back to our work here and say x is 0.6061119. And now it's asking us, what is the slope of the graph at this x value? Well, because this wasn't, first off, because this wasn't the final answer, we're going to leave that as the all 7 digits calculator gave us. But now we just need to evaluate the derivative with respect to x of -2 plus e to the tangent x at x equals 0.6061119. And our calculator will do this for us. We've seen one way to do this already, where we did those first 2 problems. But since we've already got the function typed in and graphed, we can just do it right away from that same calculate menu. So we're going to hit second, then we're going to hit trace, which brings up the calculate menu. And if you look, you could probably figure out that option 6 is the right option here, dy dx. And when you hit that, it just brings you back to the graph. And it doesn't look like it's done really anything. But if you just start typing 0.6061119, it fills it into that window. When you hit enter, you can see it tells you that dy dx is equal to 2.9609123. And we've now got our answer. 2.9609123, which is a perfectly acceptable answer on the AP test. Or if you want to, you could round it to 2.961, but no less than that. And an important thing to remember here is that if the third digit is a 0, just out of abundance of caution, make sure you include that 0. So if this would have rounded to 2.960, now if it was not a 9 after the 0, there was a 2 after the 0, just make sure you write that 0 in so they don't think that you're only leaving it at 2 decimals on the AP test. All right, we're going to have a somewhat similar problem here, dealing with a fairly similar function. This function, y equals -3 plus 2 to the power of e sine x, has 2 x-intercepts and 1 horizontal tangent line on the interval 0 to 4. We're looking for the equation of the horizontal tangent line and the point at which it occurs. And it asks us in this case to give an exact answer. So we're going to throw away the calculator for a second and just say, well, a horizontal tangent line just means that y prime needs to be 0. And we just need to find y prime. Y prime is, well, the derivative of -3 as a constant, so that's 0. And 2 to the e sine x is just 2 to the u. So that'll be 2 to the u, e sine x, times natural log 2. That's the rule for 2 to the u. And then you got to multiply by the derivative of e sine x. E just being a constant gives you e cosine x. And we want to know when that equals 0. Well, there's a bunch of things being multiplied together. So if any piece of this was equal to 0, the whole thing would be equal to 0. Now, natural log 2 is just a constant. E is just a constant. Those are clearly never going to be 0. And 2 to the e sine x is also never going to equal 0 because 2 to a power is never going to be 0. So really what we're looking at over here is just cosine x equals 0. And we're specifically asked about the interval 0 to 4. So we can include all negative values. And then we can start with pi over 2, which is definitely between 0 and 4. If you just approximate pi as 3, that's about 3 halves, which is clearly between 0 and 4. And then we might see another value of 3 pi over 2, and a 5 pi over 2, and 7 pi over 2. But as we think about it, if pi was equal to 3, we know it's more than 3, this would just be 9 over 2. So this value is more than 9 halves. 9 halves is 4.5. This is not in our range of values that we were given on our interval. So the only x value we get is pi over 2, which means we just now need to figure out what y pi over 2 is equal to, and it's negative 3 plus 2 to the e sine pi over 2. And the sine of pi over 2 is just 1, and we have negative 3 plus 2 to the power of e. So our horizontal tangent line is y equals negative 3 plus 2 to the power of e. And it asks at what point does this occur? Well, it occurs at the point pi over 2, negative 3 plus 2 to the e. So now we're going to move forward and do a second part of this problem with the same function. But now we're looking for normal lines at the x-intercepts. And then we're looking for where those normal lines intersect. So we're going to get a whole lot more of our calculator functionality in. First off, we need to find those x-intercepts. Now, again, that could be done by hand without a calculator. But since I'm telling you to use a calculator here, we might as well use a calculator. We're going to see, when does negative 3 plus 2 to the e sine x equals 0 on the interval 0 to 4? And it says it happens twice, so I'm going to just get myself set up here. I'm going to have 2 different x values where this is true. So we're going to switch back over to our calculator now. And what we'll see is we've already got this in here, y equals negative 2 plus e to the tangent x. So we'll go into the y equals and clear that and put in our new function. Negative 3 plus 2 to the power of, and then e to the x is on the natural log button, but just a regular e is second and then the division sign, and then sine of x. And when we graph this, we're going to see that it doesn't really look anything helpful to us. Right? It's showing us an x-intercept, but who knows what that value is. We have to think about what we did with the previous problem. We were zoomed in on an interval from 0 to 1, and we don't want that anymore. We actually want an interval from 0 to 4. So we could go into the window settings and change it to 0 to 4, and we will do that. But before we do that, I want to make sure we know how to just get this back to the default settings. So we're going to hit zoom. And if you hit option 6, zoom standard, it'll bring it back to the default setting for the graph, and you'll be able to see a better picture of what this function looks like. So here is our function, negative 3 plus 2 to the e sine x. And as we said, we really do want the window to be 0 to 4, so we'll go into window, change it to 0 to 4, and click graph. And we can see that there are clearly 2 x-intercepts on this interval, just like the problem said. So we'll use the same technique that we were using before to find them. Second, trace, which brings up the calculate window. We're going to pick option 2. And it says left bound. And well, we're already flashing to the left of the x-intercept that's the larger x-intercept. So we'll just find that one first. I'll hit enter. It says right bound. I will scroll over until I am clearly to the right of my function. I'll hit enter. It'll say guess. I'll hit enter again, and I'll get a value of 2.519083. There's our first x-intercept. Then I'll just do this again. Second trace, option number 2. And it says left bound, and now I'm way to the right of that first x-intercept. So I'll just scroll over the left of it, hit enter, scroll to the right, hit enter again, and we end up with 0.6225087. So we've got our two x-intercepts. Let's go back to our work for a second here. List those out. 0.6225087 and 2.5190839. We're not going to round those values at all because those are not final answers. All right, now, one thing that you're allowed to do on the AP test, if you want, to save you some time and to make sure you don't have to just type these long decimals over and over and over again, is we can store these values on our graphing calculator as a variable. I'm going to show you how to do that. We're going to call this one A, and we're going to call this one B. So, back to our graphing calculator. I got to go completely out of the graph. I'll just hit second. The mode button gives us second width. And I'm going to type in that first x-intercept that I found, which was 0.6225087. And then just above the on button, bottom left corner, there's a button that says STO with an arrow. We're going to hit that. It's going to just put an arrow out. Then we're going to choose our variable A. So you can see on my calculator, it's a little green A on the map button. I'm going to hit alpha. Then I'm going to hit the math button. And when I hit enter, it's now stored that value as A. We can check and make sure by just hitting alpha A, and it shows me that value. That would allow me to, if I needed to evaluate some fairly unpleasant function at this value, I could just hit, well, what if I needed to find A squared plus the square root of A minus 3 sine of A. A lot easier to just do that than it is to type 0.6225087 out each time. And it'll just give me a value. So then we're going to do the exact same thing with our other x-intercept, which was 2.5190839. We're going to hit that store button, STO with the arrow. This time we'll choose B and hit enter. And I like to just, out of abundance of caution, check and make sure it's stored it correctly. Check and make sure I typed the number right. Looks like I'm good. So now I can go back to my work and know that I've stored those as A and B on my calculator. And I can just, anytime I want to write this number, instead of that on the AP test, I can write A. Or if I want to write 2.5190839, instead of that, I can just write B. So next, it's asking us for equations of the normal lines. Well, in order to write the equation of a normal line, we're going to need a slope and a point. We've got the point, so we've got the two x-intercepts. But the slope needs to be the opposite reciprocal of the slope of the tangent line, which means we're going to need to find the derivative with respect to x of -3 plus 2 to the e sine x, evaluated at x equals 0.6225087, which I'm not going to write. I'm just going to write an A. And I also need to find the derivative with respect to x of -3 plus 2 to the e sine x at x equals b. Now, conveniently enough, we've already got this function graph. So if I go back into the graph, I can just hit second trace, which brings the calculate window up again. And I can pick option number 6. And I'll just type in well, actually, I'm not going to type in 0.6225087. I'm just going to type in alpha A. And it's going to give me this new value where the derivative is 4.5921992. And I'll do the same thing. Second trace, option 6, alpha B. And that's going to give me the same thing, except a negative. So I'm going to go over here and write these values in. The first one gave me 4.5921992. And the second one gave me -4.5921999. I'm just going to throw a 2 on there because I know it was the same value, except the negative. And in order to not write this over and over again, I'm going to set this equal to C on my calculator. So I'll go back over to my calculator. I'm going to quit out of the graph menu again. I'm going to type in 4.5921992. I'm going to store that as C. And I'll check again. Yep, I've got it stored correctly. And I'll go back to my work again. So now we need to figure out the equations of the normal lines. Well, this 4.92 value was the slope of the tangent line. If I want the slope of the normal line, that ought to be the opposite reciprocal. And for this one, the slope of the normal line ought to be the opposite reciprocal, which will just be positive 1 over C. Which means I should now be ready to write the equations of those normal lines. I'm going to need a new page for this. The first one is going to be y minus the y value of the first x-intercept. And, well, the y value of the x-intercept is 0, so y minus 0 equals my slope. And my first slope was negative 1 over c. And I just need to multiply that by x minus the first x-intercept, which was x minus a. And the other one will be y equals positive 1 over c times x minus b. And we're interested in when do those two functions intersect each other. So we're going to let the calculator figure that out. We're going to say negative 1 over c times x minus a is equal to 1 over c times x minus b. And we'll go into our graphing calculator and we'll graph both of those functions. So my first one, and I'm going to type in my negative, and then some of the newer graphing calculators, the functionality allows you to make a fraction by hitting alpha and then the x button next to it. So I can do negative 1 over c, and then parentheses x minus a. But if yours doesn't have that fraction button, just make sure that you put that fraction into parentheses, because it's going to follow order of operations left to right there. You don't want to screw something up. And then x minus b. And we'll hit graph. And now we can see our two lines. And when we look at it, it really doesn't look like those are perpendicular to the function at the x-intercepts. But we have to remember that the reason that is because our window settings are all messed up. So if we hit zoom 6, zoom standard, it's going to bring it back to the standard graph, which makes it look pretty good, but it's still not quite perfect. To square it up, we're going to hit zoom, option 5, zoom square. And now when we look at those, they really do look perpendicular to the function at those x-intercepts. Now, in order to figure out where a function intersects another function, we're going to use an option in that trace, or that second trace menu, the calculate menu again. But it's kind of annoying to have a third function in there. So I'm now that I don't need the negative 3 plus 2 to the d sine x, I'm just going to clear it out of there. Click graph again, and now all I've got is just the two lines. I'm going to hit second, trace, bringing up the calculate window. And you could probably imagine that if we're looking for an intersection point, we're going to need option 5, intersect. It'll say first curve. And so you can see that cursor's on the red line. Just hit enter at any point to the left of where they intersect. It'll say second curve. Scroll a ways over to the right. So you are to the right of where they intersect. Hit enter. And then it'll say guess, hit enter again. And it will give you the intersection point that we were looking for. So we'll go back to our work. And we will say this happened at x equals 1.57077963. And that would give us y is equal to negative 0.2065. This would be acceptable, or if you want to, you can write it as an ordered pair. I'll just round these, but we don't have to round them. You could leave it with as many decimals as your calculator gives you. We're going to look at one more problem today, and it's kind of throwing back to when we were doing horizontal and vertical tangent lines. But this time, in order to solve where some of those tangent lines actually are, we're going to need to use our graphing calculator. So we'll start, though, with the standard method for finding horizontal and vertical tangent lines. Take your derivative, 4x minus 12y squared y dx equals to 3x squared minus 2y dx. We'll solve for dy dx, so we'll bring the 2y over with the minus 12y squared, factor out the dy dx, and bring the 4x over with the 3x squared, giving us dy dx is equal to 3x squared minus 4x over 2y minus 12y squared. In order to figure out when this might have horizontal tangent lines, we'll just set our numerator, 3x squared minus 4x equal to 0. We'll factor out an x. And we'll use the zero product property to get x equals 0 and x equals 4/3 as possibilities. And to figure out when this might have vertical tangent lines, we'll just set the denominator of this thing equal to 0. 2y minus 12y squared equals 0. We'll factor out a 2y, leaving us with y of 1 minus 6y. And y equals 0, and y equals 1/6. So the next step, if we recall, is to take each of these values and plug them back into the original equation to figure out the ordered pairs where these tangent lines that are horizontal and vertical might occur. So we'll start with the horizontal tangent line. So we had our function of 2x squared minus 4y cubed equals x cubed minus y squared. And we were looking at when x is 0 to begin with. Well, if x is 0, all the x terms are going to disappear. And we'll just be left with negative 4y cubed equals negative y squared. Or 4y cubed minus y squared is equal to 0. We'll factor out the y squared and get y equals 0, y equals 1/4. And since we used x equals 0 here, we know that the ordered pairs we're looking at are 0, 0, and 0, 1/4. So that's a good start here. Now we'll do the same thing with our other x value, which was x equals 4/3. That's going to give us 2 times 4/3 squared. 4/3 squared is 16/9. Minus 4y cubed equals 4/3 cubed, which will be 4/27, minus the y squared. This is just a cubic. And in order to solve this cubic, we just need to get it set equal to 0. So we'll bring the 4y cubed over, positive 4y cubed, minus y squared. And then we've got plus 64/27, and then minus 32/9. And that's now going to equal 0. If you don't feel like combining the fractions together, you don't need to, but common denominator is 27, which makes 32/9 equal to 96/27. 64/27 minus 96/27 is just 32/27. And now we have a nice cubic that we need to solve. So we'll go into our graphing calculator because this is not a cubic that we're going to be able to solve easily by hand. We will, in this case, I'm just going to say, I'm going to reset this whole calculator. Second plus option 7, option 1, option 2. I now know that I'm in radians and my graph is back to everything as normal. So now we can't plug in 4y cubed minus y squared minus 3227 equals 0, but I can just put all those in terms of x and figure out the solution to that equation in terms of x. So we'll have 4x cubed minus x squared, and then minus 3227. Again, you can use that fraction button, but if you don't have the fraction button, just make sure you put 3227 into parentheses. We'll graph. It looks like it's got one solution there. We'll just hit second trace to bring up the calculate menu. We'll choose option 2, 0. It says left bound, so we'll hit enter because we're already to the left. We'll move to the right of that x-intercept. We'll hit enter. We'll hit enter one more time. And we end up with 0.7612692. So we can go back over here. This is at y equals 0.7612692, which would be the ordered pair 4/3, 0.76122692. So we found 3 different ordered pairs where we might have horizontal tangent lines. Now we're going to have to go in and figure out where we might have vertical tangent lines. So take a new page here, 2x squared minus 4y cubed again equals x cubed minus y squared. And our 2 options were y equals 0 and y equals 1/6. So now we'll take a look at both of those. So for y equals 0, we're just going to be left with the x terms. 2x squared equals x cubed, or x cubed minus 2x squared equals 0. We'll factor out the x squared. And using the 0 product property, we get x equals 0 and x equals 2. This means we've got an ordered pair of 0 for x and 0 for y, and another ordered pair of x is 2, y is 0. That's the easy one. Now we'll go back in here with y equals 1/6. If we put 1/6 into this, we get 2x squared minus 4 times 1/6 cubed, 1/216, equals x cubed minus 1/6 squared, or 136. I think I'll bring everything over again to the right-hand side. So I've got x cubed minus 2x squared minus 136. And then negative 4/216 auto reduce to a negative 154. And when I bring that over, that's a plus 154 equals 0. Or x cubed minus 2x squared. And then the common denominator there is going to be, looks like 108. So 136 is 3/108. 154 is 2/108. So negative 3 plus 2 is negative 1/108. And we'll set that equal to 0. And once again, we'll need to go into our graphing calculator in order to solve that equation. We'll hit y equals. We'll clear out the one we've already got in there. We'll put in x to the 3rd power minus 2x squared minus 1/108. You can use the fraction button or otherwise put it into parentheses. And when we graph, we end up with something that looks like this. We can pretty clearly see that there's an x-intercept over there near 2, but it's a little harder to tell what's going on near the origin. So let's start by hitting zoom and choose option 2, zoom in. And that'll allow us to zoom in around wherever our cursor is. So I'm just going to bring the cursor over kind of right between the origin and where x is 2, and hit enter. And it zooms us in. All right. It's still kind of hard to tell what's happening at the origin. So before we zoom in anymore, let's find the x-intercept that we can see. Second, trace. Option 2, 0. I'm already to the left, so I'll hit enter. I'll scroll over to the right. Go on to the right of it, hit enter. It says guess, I'll hit enter again. And I get 2.0023095. We'll write that down in a second. But now we're going to zoom in even further around that point at the origin. So zoom, option 2. And I'm going to bring my cursor pretty close over to that origin and hit enter. And well, it's still pretty hard to tell. I'm going to hit zoom, option 2, and zoom in again. And at this point, we can now see that that graph is not crossing through or even touching the x-axis at that point. So we just have one singular x-intercept for this function. So we'll go back to our work. We'll say that this is true when x is equal to 2.0023095. And the coordinates there would be 2.002. I'll just round that there, comma 16. So now we found all the locations, there's 3 of them, where we might have a vertical tangent line. And so now we have to go through and see if we got any of the same ordered pairs for the horizontal tangent lines as we did for the vertical tangent lines. So if we look, we've got 0, 0, 2, 0, and 2.00216. If we look back at our horizontal tangent lines, the only one that matches up is at 0, 0. We're going to cross that off because this makes dy dx 0 over 0. And one of our rules was if dy dx is 0 over 0, it doesn't give you a horizontal or a vertical tangent line. So we're going to ignore that one. But the other ones look pretty good. Looks like x equals 2 and x equals 2.0023095 ought to be our vertical tangent lines. And y equals 1/4 and y equals 0.761262 ought to be our horizontal tangent lines. And the last thing we're going to do here is we're going to go back in, not to our graphing calculator this time, but actually into Desmos. And we're going to graph that function we had was 2x squared minus 4y cubed equals x cubed minus y squared. And I'm kind of lazy in Desmos and don't like to type in the squares and the cubes. And this is what we end up getting. And we were supposed to have a horizontal tangent line at y, or that's not what I meant to do. Horizontal tangent line of y equals, looks like we had 0.25, right, or 1/4. And it sure looks like that's exactly where we are there. And we were also supposed to have a horizontal tangent line of y equals 0.761. And it looks like right up here, that's right about halfway between 0.5 and 1. So that should be y equals 0.761. We could just throw in some equations here. We could say y equals 1/4. Sure looks like that worked out nicely. And y equals, I'm just going to approximate it as 0.761. And we can see that it sure looks like that's a horizontal tangent line there also. And we're also supposed to have vertical tangent lines at x equals 2 and x equals 2.002. Well, in order to investigate that, we're going to have to really zoom in here. But if we zoom in quite a bit, I think we can see that there are 2 vertical tangent lines there. And one of them sure is at 2. And the other one is just a little bit past 2.002, which is exactly what we found when we were working through the problem. And that should be pretty good on the functionality for your graphing calculator with a little extra practice on horizontal and vertical tangent lines.